Hello, Nisola speaking. The topic for this presentation is real-time and the subject is an introduction. The main focus in computer system is normally to estimate or calculate a set of values or parameters. In real-time system we have an additional requirement that these calculations or estimation must be done within the correct time. So the agenda for this introduction will be time, maximum time, and time requirements. When we have time requirements, we also need to synchronize the system with the process. And one way of doing this is to divide the software into several tasks to handle sub-tasks of the challenge or problem. When we have divided into tasks, we also need to handle resources. We have a set of resources, and these resources must be shared between the tasks that we have running in the software. There's also a little comment about the difference between programming an office system and a real-time system. A real-time system should be an embedded system, so a little about what is special about an embedded system. And also, in order to understand computer systems, it's good to understand how the CPU or microcontroller is working, and especially in real-time system. Real-time system is a huge area, and in some cases it's very important to fulfill the time requirements. So there exist a lot of books about how to analyze, design, and how to fulfill time requirements. On the top here, we see that normally computer systems have non-real-time requirements or no time requirements. But if you have time requirements, you may have it for control systems, for communication protocols, and so on. And we also separate between soft and hard real-time. We will come back to that later on in this course. So in this introduction, first a little about time. So we have a process and we have a control system that is monitoring this process. So it's monitoring the physical process based on a set of events, and it must respond to these events. And in real-time system, we will have time requirements. That means whenever you have an event, you must react within a maximum time to that event. But it doesn't mean that a real-time system should be as fast as possible. You should have a good design, and you should have the estimated values or calculations within the maximum time, or what we say, the correct time. And also remember that you cannot have it very fast, because especially when you're dealing with analog sensors, you have some time delay in converting from an analog value to the digital representation. You will always have some sort of filtering. You should also always have that in your computer system when you're dealing with external signals. Do filtering. And also in distributed systems, you need to have communication protocols, which also will delay the flow of information. So maximum time is important in real-time system. Your system should react within this maximum time, and also whatever calculated or estimated values you have, they should be available within the maximum. And in order to do this, we very often divide the system into several tasks to handle these time requirements. Some system you don't have any time requirements at all, very few have only one, and many system you will have several time requirements. For example, 100 milliseconds, 2 seconds, 1.5 seconds, 10 seconds, and so on. And then you will have different tasks to handle these time requirements. To handle these different tasks, we need some sort of synchronization. First of all, we need to synchronize between the tasks and the physical process. But we also need to have some sort of synchronization between these tasks. Here they are named tasks, here they are named program. We'll come back to what is the difference, but we normally just call it a task. One task should then handle a short set or a specific set of time requirements. What happens if you have all the events at the same time? All the tasks should be running, but on a computer you can only run one or a few set of tasks. And we need some sort of synchronization to handle this. It should be synchronized with events, but also internally. It should be synchronized, for example, by using communication protocols or messages between the tasks, or what is shown here, global variables. When we have several tasks, we also need to be able to share the resources. We have a limited set of resources, both hardware and software, in the computer system and also in the process. And these should be shared within the tasks that are going to use it. For example, on the hardware we have CPU, we have memory, we have the disk, we have display, printer and so on. When it's dealing with software, we have shared memory, for example buffers. You want to exchange information. That's also shared information. And one good example is the printer. What happens if all the tasks need to print a message on the printer? It will be very messy if all of them is writing on the same time. So that has to be handled by the real-time system. We're talking about programming. In normal office systems, we have a sequence of operation that should be done. You will start the program, you will do a set of operations and then end it. However, in a real-time system, the application needs to run in parallel with the process, so it's event-based. So first of all, it has to run as long as the process is running, and whatever event or combination of events that is happening, it has to deal with it. So the information here is more event-based in a real-time system than in an office system. So real-time system is very often an embedded system. An embedded system means that you have a computer that is encapsulated by the device it controls. That means you have a limited set of tasks. So in order to fulfill the time requirements, you need to know how many tasks you are running. In that case, it means that a real-time system will very often be an embedded system, because you need to have just a limited set of tasks to be able to calculate or figure out the maximum time. But on the other hand, an embedded system don't need to be a real-time system. We will come back to that. The last thing is the CPU. We have been talking about several tasks that are running. They are running in parallel, or it seems to be in parallel, but we have what we call a scheduler that is controlling which task to run and for how long. So in order to understand how a schedule is working, we will look very short into the CPU or a microcontroller. You have an interface to the memory. You have what we call a program counter. That's the counter that, or the address that is saying in which memory we should read or write. Then we have an instruction fetcher, instruction decoder, a set of registers, and an ALU, arithmetic logic unit. So we will read something from the memory, decode the instruction, save some of the values in register, and then based on the instruction we can, for example, summarize, subtract, multiply, or use the combination of registers as a new address to access memory, for example. So we very often talk about the state of the CPU, and that's the content of the program counter and the content of the registers.